In the previous lesson, we learned that when a charged particle enters a magnetic field, it experiences a force that will change its direction. We also learned the right-hand rule, the first one, that allows us to predict the direction of deflection based upon the direction of the force on that charged particle. This time we're going to take that idea and extend it in several new directions. One of which is if we have a charged particle going through a wire, remember you need mobile charged particles. It's technically not electrons here, but again we define current as being the positive charge moving through a wire. We're going to see that a force is going to be exerted on that wire as well. If you look at this picture on page 630, notice the direction of the magnetic field. Is it into or out of the page? If you remembered correctly, the X's, green X's, mean that the magnetic field is going into the page. In the middle picture, picture B, if the current is moving from the bottom to the top of the page through the wire that is resting on or in the magnetic field, and you use your right-handed rule, place your fingers, and again we're using my right-handed rule, not the one in the text. If your fingers are going into your book, into the page, like an arrow, and if you put your thumb in the direction of the current, which would be headed towards the top of the page, you can see that the palm of your hand is directed left, which will push the wire to the left. And if you're thinking about this and anticipating where we're going, you're going to see that this is the basic principle behind an electric motor. That if we make electricity go through a wire that is in a magnetic field, it will move the wire. And somehow the engineers have to figure out how can you get the wire to continually move without getting all twisted up, because that's what a motor does. In picture C, we reverse the direction of the current. So, again, your fingers are going straight down into the page. Your thumb this time is pointed towards the bottom of the page, and now your palm is pushing the wire to the right. Obviously, I hope it is anyway, that the amount of this push, of this force, will get stronger if the magnetic field is stronger. It will also become bigger if the current is greater. And the longer the wire that is in the magnetic field, the greater the force will be as well. We put these three pieces of information together, and you get equation 19.6. If you're not moving perpendicular to the magnetic field, but at some angle, then the force acting on the wire will not be as great. And that's why we throw in the sine theta in order to reduce the magnitude of that force. One practical application of this would be how a speaker works, at least the kind of speaker, the older kind that has the paper cone that can oscillate in and out. You might remember our unit on sound where we had a speaker hooked up to our signal generator, and we reduced the frequency to a few cycles per second, and you could watch the paper cone move up and down because it was oscillating so slowly. In this case, you'll notice some brown X's or back of arrows underneath the gray part of the cone. That means, in this case, that the current is going into the page, wrapping around the backside of that gray cylinder at the base of the cone, and coming out towards you, that's the orange dots, above the gray cylinder. So the same technique that we use for designating magnetic fields going into and out of the page, we can use to designate currents going into and out of the page. So what you have here are 3 loops of a coil or solenoid that's wrapped around the cone part, the cylinder part of the gray cone, the paper cone. And in each case, the wire is going into the page below the cylinder and out of the page towards you above the cylinder. Meanwhile, the green arrows are going from the North Pole magnet, which is in the middle of that cylinder, towards the South Pole that is both above and below that gray cylinder. That means that the magnetic field is going from the middle of that cylinder outward, both top and bottom. So if we think about the force that's going to be exerted on the paper cone, use your right-handed rule and begin at the middle of the gray cone, the gray cylinder, and have your fingers going in the direction of the green arrows. Now have your thumb, representing the direction of the current, coming out at you into your face. Again, this is above the gray cylinder, which is the base of the gray cone. You'll notice that the palm of your hand is pushing to the left, which means that the paper cone will also move towards the left. If we look at the bottom of the gray cylinder, and again, this time you have your fingers going from the center of the cylinder directed straight down at the South Pole for the magnetic field, and now turn your hand so that your thumb is going into the page in the direction of the current, the orange X's. Then your palm, if you haven't broken your wrist by now, is pushing again the paper towards the left. So as the current is going through this solenoid, these 3 loops, the cylinder, the cone, will go towards the left. When you reverse the current, the cone would go towards the right. And the faster the current reverses, the faster the cone is going to go left and right and left and right, creating pulses of air that eventually would be over 20 compressions per second that would begin to be in the audible range of human hearing. This would require alternating current. At the bottom of the page, example 19.5, we consider what happens when we have current in a wire that's in the Earth's magnetic field. So instead of the magnetic field being created by an electromagnet, or like in the previous example with the speaker, a permanent magnet, we haven't talked about electromagnets yet, this time the source of the magnetic field will be the Earth itself, which would be kind of weak, about 1/2 of a 10,000th of a Tesla. So imagine that we have a wire carrying a substantial amount of current, 22 amps, more than you would typically find in a wire behind the wall that connects your outlets. And it's going from west to east. And then we're going to assume that the magnetic field of the Earth on this part of the Earth is also horizontal, but it's directed from south to north. So again, if you want to put your fingers going from north to south and your thumb going from west to east, you will find that you're going to get a force acting on that wire And the goal is to get the force acting on the wire to be equal and opposite to the gravitational force that's going to be pulling the wire if it were to fall down towards the surface of the earth. Now we can calculate that force using the equation BLV, and we're at 90 degrees, so we don't have to worry about sine 90. And if you used your right hand correctly, you will notice that this would be pushing the wire upward as the current is going through the wire in the Earth's magnetic field. Gravity, of course, is going to pull it downward. And we can actually calculate what that gravitational attraction would be if we remember how to find the cross-sectional area of the wire, which is 2.5 millionths of a square meter, times the length of the wire, times the mass of the wire. In section 19.6, we consider what happens if we have a loop, or simplistically a square loop, instead of a circular one, that's in a magnetic field. Now this diagram is a little tricky, but it paves the way for understanding how the opposite of a motor, which is an electrical generator, might work. Both of these principles, that wires moving in magnetic fields create current, which we're going to learn about later, and wires with current in them that are in magnetic fields are going to move, are the basis behind motors and generators, which is the basis behind so much of the technology in the first half of the 20th century. So in picture A, we've got a loop, a square loop. The magnetic field is going from north to south. The green arrows tell you that's from left to right. And your current is going counterclockwise. Down on the left side, across at the bottom, upwards on the page on the right, and to the left at the top. So if you put your fingers of your right hand going from left to right, and on the left side of the box, if you have your thumb going down, you'll find that the palm of your hand is facing straight up. On the other side of the square, the right side of the square, in picture A, you're going to see that your fingers are going from left to right again, but now your current is going up the page, and so now the palm of your hand is facing straight down on the right side of picture A. And as a result, the entire square is going to rotate, pushed up on the left, pushed down on the right. Now, if we take that picture and look at it from the edge, kind of like if you were to take your iPad or your laptop that's lying flat on your desk and now put it on the edge of the computer so that the top edge is sticking straight up into the air. That's what picture B looks like. And now you can see the upward force, which in picture A was out of the page. In picture B is now going towards the top of the page. And the right-hand part of the box in picture A is now on the right side of picture B, but its force is going down instead of the other direction. And so this whole thing is going to experience a torque. And that torque is going to twist this solenoid, this loop, this square loop, in the clockwise direction. It'll be perpendicular to your magnetic field, the green B, in picture B, but it will be at an angle in picture C. and not as much. And that's why we would need sine theta attached to our equation 19.8, which says that the magnitude of the torque that's going to cause this loop or many loops of wire to spin in a magnetic field logically depends upon the strength of the magnetic field B, how much current is going through the wire, and the size of the solenoid or loop or loops represented by the cross-sectional area that is in the magnetic field. So your torque equals BIA. We make a minor adjustment to this when we come to equation 19.10a and b, and that is, it's very unlikely that the number of turns of wire of your solenoid or coil or loops doesn't change, and the size of your solenoid or loop also doesn't change. And if the current is constant, we can say then that the current times the cross-sectional area times capital N, which is the number of turns of wire in the solenoid or the number of loops, is always going to be the same value, which we'll call mu, and that is known as the magnetic moment. You might remember that way back when we were studying angular velocity and angular acceleration, we had the rotational inertia, or the moment of inertia. This is similar to that. This is a magnetic moment. And that's a constant, and it can be represented by a vector designated by mu, and it's always perpendicular to the plane of the loop. And so BIA becomes mu in equation 19.10b. The drawing for this is on the next page, 634. And you can see that the loop, where the current is going counterclockwise, is in a plane, the XY plane, and therefore the vector representing IAN is perpendicular to that, represented by the red letter going up. Now let's apply this to something very, very practical, an electric motor. And electric motors are all over the place. And we keep coming up with new ideas for using them, such as electric cars again. Now, this is going to be a little bit hard to explain without you actually looking at a simple motor. This is where you might want to go online and find a video that might show you this in action. I'm going to blow it up here. And here you have a square loop, and instead of multiple turns of wire, for simplicity's sake, we just have one wire. It goes from left to right, entering the magnetic field, takes a sharp left-handed turn towards the North Pole, goes across the North Pole, takes a right-handed turn, goes towards the South Pole, comes across the South Pole, takes a right-handed turn, and then goes back to what we call the brushes, or that are part of the split ring commutator, which I'll mention a little bit later. So in other words, we have one loop of wire that's in a magnetic field. The magnetic field, by convention, is going from north to south. The current is represented there by the red letter. And in order to keep this loop of wire from twisting all up as it rotates in that magnetic field, experiencing a force on both sides of the loop, we attach it so that it can slide smoothly across brushes. Each wire is connected to half a ring, a semicircular ring, and that ring brushes up against the brush. That's why we call it a brush. When I had some slot cars way back as a boy, it was an actual brush of many, many fine wires. Here it's just represented by a little block. But they're not welded together. The semicircle commutator, the split ring commutator, can smoothly slide against the brush. Now, notice that it's connected to a DC power source. As the positive charge moves counterclockwise from the positive DC power source up towards the brush on the right side, the electricity goes through the brush into the right-hand split ring, takes a right going towards the south pole of the magnet, goes across the space where it encounters where the red arrow is, goes across the north part of the magnet, comes across and back down towards the middle, and back to the left-hand commutator, which is brushing up against the brush. And then the electricity returns to the battery without any voltage left, plumb tuckered out. That explains where we get the direction of the current. Now, back to the space between the magnets. If you put your fingers representing the magnetic field, and again, we're using my right-hand rule, not the books. You're welcome to use the books. If we put our fingers going in the direction of the green arrows and our thumb in the direction of the red arrow, that forces me to have my palm going towards the left, pushing against the wire that's next to the North Pole and shoving it towards the South Pole. Meanwhile, the other part of the wire that's next to the South Pole would have the current going into the space behind the South Pole. The magnetic field is still going in the same direction, but now that's going to push the lower part of the loop away from the South Pole, just like the upper part of the loop is being pushed away from the North Pole. In other words, it's going to be twisting clockwise. And as it twists, the commutators are going to twist until they're no longer in contact with the brushes that you see in the picture, but now come in contact with the other brush that the previous commutator was in contact with. And this allows the loop to continue to spin inside the magnetic field for as long as it's hooked up to the battery and as long as the battery has juice. In other words, this is an electric motor. I'll let you think about that for a little bit, and you might want to even pause the video and think about what's going on there. Now, Ampere's law, 19.7, shows another phenomenon, and that is that if you have electric current going through a wire, lo and behold, you actually create a magnetic field. Not a magnetic field that was already there, but you're inventing or creating this magnetic field from scratch. And we're going to be getting another right-hand rule at the bottom of page 19.7. And in this right-hand rule, imagine that we have a wire coming up through a platform Could be a piece of paper, thin piece of cardboard that the wire has punctured. And we put little teeny tiny magnets, maybe about the diameter, I should say compasses, not magnets, compasses about the diameter of my baby finger, and we put them on that surface as close to the wire as we can get them. Now, initially, in picture A, all the needles of those compasses will point in the same direction, towards the Earth's North Pole. But now we turn the electricity on, and now we have current going in one direction through the wire from the bottom to the top in the direction of the red arrow. You'll notice that all of the compasses are now showing a deflection. They're no longer pointing to the Earth's North Pole, but they're pointing to some other magnetic field. And so what we would do here with our right hand, this time put your thumb in the direction of the current, which is going towards the top of the page, and you can see that the natural curvature of the fingers of your right hand are going to go counterclockwise around the wire. That means that they're going from north to south continuously around the wire by the convention that we have adopted. We have created a magnetic field that encircles the wire as direct current goes through the wire. We can actually use this to calculate the strength of the magnetic field that we have created. And as you might imagine, the strength of that magnetic field is going to depend upon mu, the permeativity of free space, which we had in the previous chapter, what the material is that surrounds this coil. It depends upon the current. The stronger the current, or the more current going through the wire, the stronger the magnetic field will be. And of course, the closer you are to the wire, the stronger the magnetic field will be. So your magnetic field is inversely proportional to R, the distance from the center of the wire. We can rearrange those terms and come up with Ampere's law. And end up with an equation very similar to the one that we just talked about. And I'm going to pause right here and stop and save this.